Take a drink of water first. Okay, thank you for the kind invitation to talk about my research that I've been doing with a company called Recycling Technologies, basically trying to deal with all the waste plastic that we have around, not just in the UK, but in Europe and in the world. Okay. So how much do we like plastics? Okay. Well, since the 1950s, you can see the increase in the amount of plastics has been used day on day. Year on year. And for the people interested, around about 1975, miners' strike, bit of an economic recession, and similarly 2009, you can see the dips when the world consumption of plastic went down, which is a bit of a godsend for us if you're looking from my point of view. We don't want these plastics. Obviously, from a business point of view, we want them, but from an environmental point of view, we don't. So all the plastics that we use generally end up in something that looks like this. This is something you're probably not familiar with, but if you were to take your green bin and shake it across your garden, you may have something that looks like this. So you get a lot of mixed plastics, okay? The problem here is the mixedness of this plastic. So your recycling plant will deal with a certain amount of this plastic. It deals with two types of plastic, so basically your Coke bottle and your water bottle or your milk bottle tend to get recycled and reused into something else. So we're left with lots and lots of other plastic that we don't know what to do with. So where does our plastic come from? Well, it comes from lots and lots of industries, so construction, packaging tend to be one of the largest sectors. And all this equates to 46.4 million tonnes of plastic waste, or plastic that is generated in the EU, and Switzerland and Norway. Okay, so it's E27 countries, and these other two countries. So what happens next? We send 24.7 million tonnes of this plastic to a recycling plant, which is great, okay? You're already seeing there's a bit of a deficit there to start with. Okay, so when it goes to our recycling plant, 14.3 million tonnes of that plastic waste I said that is in your bin, not all of it gets recycled. Only 14.3 million tonnes gets recycled of that plastic. Another 10.4 million tonnes disappears somewhere. Okay? Goes to landfill. So let's just add up all the maths. We also have another 21.7 million tonnes, the difference between here, okay, that's there. So this equates to basically 69% of plastic that's in the wrong place that we need to do something with. Okay, we've dealt with our recycling here. We can recycle, reuse, turn it into useful products again, or we can turn it into energy. And some countries follow this route more than other countries. So what does this all mean? Okay, so basically we have about 32 million tonnes of plastic waste that we can do something with. If we were to convert this all into energy, okay, if we were to basically crack all the bonds, and I'll come back to that in a minute, what that actually means. If we were to crack all the bonds, we could generate 84 gigawatt hours of electricity, which if you look at the energy consumption for the UK, this would basically power all the energy required for the Greater London and the South East, and more, just from all this waste. Okay? But obviously we need a technology to be able to do this. Taking this a little bit further, just expand on this, the amount that's recycled. This is 57.9% of the material that gets recycled, so this is 57.9% of the 24 million tonnes that gets into our recycle lines. Let's look at the countries across Europe, and some do it better than others. Okay, so I've highlighted the UK. We tend to follow people rather than set precedents in this area, but we recycle around about 22% of our material, and about 9% we actually burn as a fuel, because it's very high calorific value. Our polymers, we can burn them as a fuel. So we recycle about 31%. So we're below the EU average. Whereas Germany, this is largely from a precedent set from the country. They don't want to put any waste to landfill. Actually recycle similar amounts to the UK, about 30%, but they essentially burn the rest of the fuel. So they burn it in very, very large power plant generation facilities, where they usually heat water and raise steam and then put it through a turbine. That in its own right has losses, so you're starting to lose some of the energy that you could potentially use. They're also very, very expensive, and I said, especially in Germany, they have to have support from the government to make these things work, okay? Because the return from investment is very, very low on these. So they usually run at a loss. Problem with these, when you burn the plastics, they also create a lot of heat. So what do you do with the heat? You need to do something with it. So the idea would be to have your great big power plant and to have it next to a housing estate. So the houses could actually use the heat to heat their homes, which they do. But who wants a great big dirty recycling plant in the middle of your housing estate? So we need to think a little bit more smartly how we actually can tackle this. So people can still use these plastics and get the energy from them, but don't have to have all the side effects, all the things we don't want about it. So what we've suggested is a bit of a schematic here, is our system. It's a little bit smaller than these very, very large power generation plants, and they can fit within existing recycling facilities and manufacturing facilities. So basically we have a treatment process, so this is one of our small units, 7,000 tonnes per annum, comes in, we treat it to get it into a particle size that we want, that we can feed into our special unit here. So this is where all the science goes on. So this is the research that I've been doing at Birmingham, is basically making this work. Okay, and I'll come back to that in a minute. The energy that comes out will have, obviously, a calorific value, which we can put through a big engine, essentially. We put it through a great big diesel engine, or very similar to a ship engine. Okay. And we can create energy from this. Good thing about this, because they're small, because we can fit them into localized facilities, we don't have to transport lots and lots of plastics to one location site. So we're cutting down on emissions from transportation as well. So let's look at the values. Let's look at the business case around this. We sell these units for about 2.5 million. But if you look at how much you're actually saving, okay, at the moment, because it goes to landfill, a lot of the companies that actually recycle do not want to put these materials into landfill because they have to pay a landfill tax. So a lot of companies are actually storing these materials in warehouses at the moment until the landfill tax or something comes along that can deal with it. So you're going to save between £80 and £100 per tonne, depending on the UK. So if you're processing 7,000 tonnes per annum, you can save £560,000 straight away. Okay? Because you're putting it through an engine and creating 2.7 megawatts of electricity, the end of it, which is enough to power 5,000 homes in the UK typically, you can also sell this electricity to the grid, so you're going to generate just over £1 million in electricity. And because you also produce some heat as well, we can sell the heat obviously to the local facilities, because obviously we'll generate heat. We can sell it to the industrial estate and maybe to some houses, but because it's not this great big dirty power plant, it's a smaller unit, people are generally more acceptable to its use. So you can also save on heating costs about £380,000 a year. So it all stacks up. So over about 15 months, you can get a return on your investment quite quickly. So this all sounds great, doesn't it? You think, great, I want one of these. I'm going to get my checkbook out. So everyone must want one of these, yeah? That is our belief, and probably your belief. So we can build enough machines, we can dot them around the globe, and we can save the world from drowning in this waste plastic that we don't know what to do with, which has a very, very good use. However, I touched on this at the start, this is where the pig's ear comes in. This waste is heterogeneous. It contains lots and lots of different plastics, and these plastics have different calorific values. So if you're trying to produce an output that has a steady calorific value to go into your engine, so your engine runs at a constant rate, it doesn't really happen unless we do something with the technology. Okay, so this is where it all falls down, but we have answers to it. What your energy buyer doesn't want is variability, and this is a big thing that you see with renewables, is the variability in power, keeping a sustained power source all the time. So when the sun doesn't shine, can you store the energy, for example, as we saw? You can. Because your waste also has lots of other chemicals in it, it's not just these polymeric materials, which are, if you think back to your organic chemistry at school, carbon and hydrogen, lots of repeat units make these polymer chains, okay? But there's lots of other things within them, especially in glues, for example. You get silicons, you get sulfurs, you get chlorines, especially in polyvinyl chloride. So all these have to be treated. So we have a filter section here, because if we let chlorine build up, we can get hydrochloric acid being formed, which will make our reactors fall apart or our system fall apart. But more importantly, things like silicon can react with oxygen in the engine and make sand. You obviously don't want sand in your engine. So there's lots of challenges that we've had to address during this research, and we believe we're at a position now where we can actually go forward with this. So in answer to the question, can you make a silk purse from a pig's ear? We believe you can by some clever technology. And this is just in brief. We have a very dynamic system, so it can react very, very quickly. So our reactor can respond to the demands of our engine. So we get this constant supply of fuel to our engine in terms of its calorific value. So to just talk you through the graph, these are just carbon units. So this is methane, CH4, natural gas, large component of natural gas, and ethane, that we can burn. It has a very high calorific value. Obviously, to crack our long polymer chains down to these units requires a lot of energy. Okay? So what we like to stop at is something where near the green line, about our C6s, so C carbons in a chain. So very similar to benzene, for example, that you find in petrol. So it burns quite nicely. So during our first cracking process, so when we start to break all the chains, if we end up with something on this diagram that centers around C11, to make our process sustainable, so we get in a higher calorific content, rather than going down to the calorific content here about 44, we want it up at 45, so it's constant, we would crack the chains further in the process to get a constant supply of fuel going in to our engine. Okay, so in summary, we believe now we have the technology that we don't have to deal with all this waste plastic anymore. There's the technologies out there that we can find ways to get around storing plastic. It has a high calorific value. It is a very good fuel if the process is there, and we believe it is. And we don't have to spend a vast expense of money to do this anymore. It doesn't have to be located in very, very large buildings. And because of this, it can be applied in lots of industries that have a waste that need to be dealt with. Okay. So I'm just going to throw this question out to you. A lot of governments, especially in the UK, are on about reuse and recycle, i.e. turn something useful, your bottle, into another bottle. They don't always look at the obvious solution, basically turning your bottle into energy. Okay? So we've done some calculations, and we're saying for each kilogram of plastic that's diverted going to landfill, we basically save 1 kilogram of natural gas being burnt. Okay, so we're basically reducing the amount of carbon that people are putting into the atmosphere. This is based on these figures, and if you can see them, so we say that 1 kilogram of plastic has a general calorific value of 31 megajoules per kilogram, so relatively high energy content, similar to coal. And our process works at 65% efficiency, so that's about 20 megajoules of energy, whereas gas has a higher calorific value, but the processes that actually burn gas are very inefficient, down to about 39%, and the comparative figures equate to about 20 megajoules of electricity as well. So this is where my analogy comes from. Okay, so thank you very much for your attention.
Thank you very much, Gary. Now, any questions, and did everyone remember their A-level chemistry? Yes, there's a hand up there.
Of consignment that comes into your plant, how much plastic is recycled and used for something else, and how much is turned into energy, i.e. burnt? Okay,
well, when we say it comes into our plant won't exist till 2014. We've just taken the first order for the first plant. So our aim would be to try and get hold of all that waste material that is going to go to landfill. We wouldn't touch the material that already has a current use economically that can be then reused or re-engineered into another milk bottle or another Coca-Cola bottle. So we wouldn't touch that. So we'll be aiming for this 69% of material. In the UK, obviously that was across Europe. In the UK, it's about nearly 2.5 million tonnes of plastic waste that we can get our hands onto.
Anything else there? Yes, I can see a hand at the back, right under those very nice bright lights. I can't actually see who's on the hand.
Thanks very much. It's Chris Hocking from Deutsche Bank. I'm just trying to work out, if dealing with all the different types of plastics coming into the unit is so difficult, why not speak with Coca-Cola and get them to make all their bottles out of the same material?
They're made out of that material because it has a certain quality that they're looking for. They're looking for opaqueness in their bottles, whereas milk producers have always gone down the route that you don't have to see your milk. So they're doing it from a marketing point that people want to see their drink. And I'm doing a lot of research into biodegradable cling film. The problem with cling film at the moment is not biodegradable, but trying to make that biodegradable is very, very difficult because it has very unique properties. And what all we end up with all the time is something that's quite opaque. So you take it to the consumer and they want to, so when you buy your pack of tomatoes, you don't want this cloudy opaqueness on your tomatoes. You want to be able to see your product. So this is the challenge that we're faced of. It's the public perception of what a product should look like on the shelf. And if you change that, they will go somewhere else. They'll go to another competitor. So I think we're stuck with how Coca-Cola want to market their products.
And are the key manufacturers, are they sympathetic, empathetic to wanting to close that loop? Or is it truly the consumer that's driving that agenda?
No, you'll find that supermarkets have agendas for their suppliers. Their suppliers need to tick green boxes essentially. So if you have a supplier that doesn't have certain legislations in place or acts to act environmentally in how they produce their goods, then they can essentially go elsewhere to find another supplier that does tick this box. So suppliers to supermarkets now are very, very sort of keen to actually tick these boxes. So they can go back and say all the energy that's been used, all the materials that's been used in a process or in a product actually gets used for something at the end rather than just lying stagnant in a warehouse or in the ground.
Gary, could I just follow up a sort of point from the first question, really, which is whether, in a clever way, you don't solve one environmental problem and create another. And I'm thinking particularly about natural gas and the fact that it is captured when you make the bottles as a feedstock. And then, of course, you're proposing that you would release some of it back into the atmosphere, which has been one of the big concerns that we've been trying to address. I suppose it's the equivalent of robbing Peter to pay Paul.
That is true. You will produce some emissions from the process, but with the carbon capture that's available these days, if you look at the power generation plants for coal-fired power generation, are much less polluting than they ever were because of carbon capture facilities. And these plants do have the current.
And you're sure that the margin of capture then makes up for the, well, basically what you're releasing compared to what you're saving?
You've got, I suppose it's one of those things if you don't do anything with it, it's still going to be there. And there's a lot of energy gone into the processing of that plastic in the first place. So you might as well do something with it. Rather than burn natural gas, this is my point on the last one, rather than take a new source of natural gas from the North Sea or from Russia, we can actually burn these plastics to provide the same amount of energy.
Yes, there's another question. Thank you. There's another question at the front. So.
Nigel Kershaw, CEO of Big Issue Invest. I'd love to invest in it, but
he won't stop you.
I know what I'd do, because I think any of the profit we'd make, I would like to put back in actually going upstream and solving the problem why it exists in the first place. Because I think, although I think you have to do something like this, actually what we have to do is start changing how we produce, how we consume, and the rest of it. And now if you look at the convergence between environmental and social, and you've only got to look at a famine or water or whatever, unless we start to do that. So I think as a short-term solution, absolutely yes. But as a long-term solution, we really have to get our energies into manufacturing and how we consume if we're going to go and essentially invest in this to put ourselves out of business.
Yeah, I totally agree with you. It's a short-term interim, probably a 10-year plan, hopefully. I mean, if you saw the first figure, where the use of plastics over the last 50 years has been increasing year on year on year. We need to do something with that so we reuse more of that plastic. I mean, everyone at Hope, there's figures on mobile phones. People around the world have 3.5 mobile phones in their drawers somewhere, which is a lot of plastic and a lot of rare earth metals that need to be reused. So still we start thinking about how we tackle these problems. The problem is we make things too complex to basically reverse engineer to actually take back to pure components, and they're a lot easier to process. But when we have this mixed plastic waste, I think this at the moment is the only alternative that we can go.
You want to burning to do another one, or should we let Gary off the hook? Thank you very much.
Thank you.